I'd like to thank conference organizers for this opportunity to talk today. My name is Trevor Tucker, and my presentation is Doppler ultrasound measurement of central arterial stiffness and elasticity in cardiovascular diseases. Am I being heard well enough out there, please?
Yes.
Thank you. Okay, a comment about arterial stiffness and cardiovascular diseases. Arterial stiffness is a long recognized biomarker of cardiovascular diseases. The gold standard measure of arterial stiffness is called the carotid to femoral pulse wave velocity. The World Health Organization has identified cardiovascular disease as the leading cause of death globally. So measurement of arterial stiffness or elasticity is an important measure. A comparison now, or a function of the atherosclerotic cardiovascular disease risk as a function of this measurement, pulse wave velocity. It's indicated in this graphic, where the vertical axis is the atherosclerotic risk assessment number associated with the American Heart Association model. The horizontal axis is the measurement of pulse wave velocity. You see the very strong correlation. So measurement of pulse wave velocity in the arteries, particularly the central arteries, is very important in CVD risk assessment. The measurement's carried out like this with a couple of pressure sensors, one in the carotid, one in the femoral. Measure the time distance between the pulses that get to those 2 points, and the distance between them becomes a velocity. So this thing called velocity is actually taken almost 1 for 1 as stiffness in much of the medical community associated with arterial research. But the pulse pressure measurement, it requires measurement on 2 points, carotid and femoral. Requires specialized equipment for carrying out that measurement. Because it's a rather cumbersome and time-consuming measure, it's rather difficult to carry out within the 15 minutes allocated most clinical examinations. And it is also a measure of a number of arteries. It's a global kind of measure from the carotid to the femoral. However, the correlation between that measurement and cardiovascular disease is sufficiently high that it's been researched for a considerable number of years, endeavoring to develop a scheme that measures arterial stiffness within the clinical environment. I'd like to go back to the fundamentals now and examine the stiffness versus elasticity. And in common usage, stiffness in common language is a measure of the resistive deformation response to an object when an external force is applied. In comparison, elasticity is a measure of the recovery response of a deformed object when the external force, which causes the deformation, is removed. So there's some subtle difference between stiffness and elasticity in this. And I demonstrate that in this it's a pulse Doppler measurement of flow in a central artery. It's a rather idealized one with relatively little in the way of pulse reflection, but you can see that leading up to the systolic peak of velocity, one would interpret that maybe as a stiffness response, whereas after systole, that would be the elastic response or the recovery, the transient response after the impulse is over and the aortic valve closes. And I now show an ideal flow wave that is calculated using this equation and comparison to the measured flow. And you see there's a reasonably good match there. So I want to talk now about this equation. And it's what I would call here an ideal damped resonant frequency, and it's composed of 2 components. One is an exponential decay shown in the larger dashes, and the other is an oscillatory component shown in the smaller dashes. And together, those make up the combined transient flow response. So the dr the damped resonance frequency, and there's a damping coefficient, a natural resonance frequency, and I'll show the relationship between those three parameters in a moment. But there's a key assumption, or two key assumptions in this. One is that the impedance to viscous resistance is negligible. And the second is that corresponds more or less to a diameter of artery of greater than 6 millimeters. And the other is that there is no reflected or antegrade flow pulse from reflection from things like stenoses. So the calculation now of these values, the damped resonance frequency is related to the time between the, I'll go back one slide here. The peak of velocity at systole is V2. The peak of overshoot is at V3 and times T3. So the damped resonance frequency is given by the relationship between the time difference between the two systole and overshoot peaks. The damping coefficient is given by the relative peak velocities, and the natural resonance frequency is dependent on those two others by this equation. But in this, the natural resonance frequency becomes a new measure of the response, or the arterial elasticity of that artery. And notice that it's a relatively simple measurement. There are two independent unknowns, and they're solved by measuring 2 points on that waveform, the peak at systole and peak at overshoot. And it turns out, through a thing called the Mohs-Korteweg equation, that the standard of pulse wave velocity is related to this new elasticity measure of natural resonance frequency by L, and L is the length of the primarily what I call primarily elastic artery, the length of artery in which the viscous resistance is negligible. And that corresponds more or less to the sum of the thoracic aorta, the abdominal aorta, the iliac, and into the femoral. And it's a distance for which the the viscous resistance to the elasticity is negligible. And it's primarily for those arteries greater than 6 millimeters. And the length of that primarily elastic artery is 50 to 60 centimeters. And now compare a theoretical predicted result to a measured result. This is taken from the paper by Hashimoto in 2010. And it shows three curves. One is the measured curve. This is aggregate or an ensemble average of 132 measurements on 138 human subjects. Then I compare that to the ideal, what I've called the ideal, which is the predicted damped resonant pulsatile flow velocity wave. And between these two, there is a residue. So the amount of mismatch between the measured and the ideal gives rise to a variance, which may be a measure of the development of sclerotic plaque or a stenosis. It's actually also caused by unmatched bifurcations, trifurcations, and like. Now, these are measurements taken from that previous graphic where Hashimoto has provided us with these numbers of measured systole and overshoot velocities and times. And from this measure, we can compute the damping coefficient for that wave. And from this measure, we can compute the damped resonance frequency. And from the damping coefficient and from the damped resonance frequency, we can calculate this new natural resonance frequency. And then with this equation, pulse wave velocity equals natural resonance frequency times arterial length, where the arterial length is taken here to be half a meter. That gives us rise to a very close match, 7.85 versus 7.9, as measured by Hashimoto. And it's a new way to come up with pulse wave velocity. So all those databases on pulse wave velocity and so on can be related to this new measure of elasticity of natural resonance frequency. The match now between predicted and measured is a good visual match between the waveforms. There's a good match between the predicted and measured pulse wave velocities. And this exploratory study indicates that further work is called for, and much of it needs to be independent. It can't be done by myself. It must be done verification that they've not made mistakes in the derivation of the equations, independent validation by comparison of predicted results with measured results, and to further extend it to get rid of this rather ideal case of no pulsatile reflection to include pulsatile reflection. And that is all in the cards in terms of the physics of the situation. So what this does then is it provides a new application for Doppler ultrasound, an application that Doppler ultrasound cannot currently measure arterial stiffness. Those ultrasound systems are deployed globally, which now then allows for measurement within a clinical environment of a wide number of ultrasound systems. And not only that, but the ultrasound can measure these deeply set arteries like the thoracic, the abdominal, iliac, femoral, coronary, and renal. So it now opens the door for a bunch of new measurements using a new technique in a clinical environment. The comparison here is natural resonance frequency. It can measure a single location and in deeply set arteries using Doppler ultrasound with wide clinical applications compared to pulse wave velocity, which is a global or non-local stiffness measure. It's applicable where pulse pressure can be measured on the surface, particularly carotid and femoral. And it's a specialized measurement, specialized equipment, and cumbersome and time-consuming. And it has limited lab application. But pulse wave velocity can be determined from natural resonance frequency, and that's a big eureka for me. I didn't expect that result, and I was quite delighted when I found a relationship between pulse wave velocity and natural resonance frequency. So here are my final comments. Doppler ultrasound, pulse Doppler ultrasound, is an enabler for the measurement of central artery elasticity, but now in a clinical setting. And I guess my final comment is this is just the beginning. I welcome your follow-up inquiry if you're a person in the artery stiffness business. This represents a completely new paradigm from the old pulse wave velocity. Requires a bit of an expansion of that paradigm. It's no longer pressure, it's flow, no longer distension of the diameter of the artery, and it can be measured at a single location. That's it for me. I welcome any comments or questions.